when I introduced the Fourier transform, I discussed that although the Fourier transform is always a perfectly valid and 100% accurate reconstruction of or representation of the data in the frequency domain, the results of the Fourier transform are only really easily interpretable when the signal maintains some stationarity over time. And stationarity means that the statistical and the spectral characteristics of the signal are not really changing very much over time. And of course, we know that this assumption is violated in neuroscience data, and in fact, it is the non-stationarities, it is the changes in the structure of the data over time that we are specifically interested in. And so, therefore, computing the Fourier transform over the entire signal doesn't really make a lot of sense, and it doesn't really produce very easily interpretable results. And so we've discussed now two different methods for obtaining time frequency information out of the time domain signal. One is Morley wavelet convolution, and the second is filter Hilbert transform. Now, the original method actually for doing time frequency analyses is to use the Fourier transform, but to compute the Fourier transform only on small time windows of the signal, rather than over the one Fourier transform over the entire signal. And this method is called the short time Fourier transform, and that's what I'm going to introduce you to today. In fact, the short time Fourier transform is a very straightforward method, and probably even if you had never heard of the short time Fourier transform, if you knew about the Fourier transform and you thought about doing time frequency analyses, you would probably come up with this solution. So here's how the short time Fourier transform works. Rather than computing the Fourier transform over the entire signal, you just pick a small window. So here this is 500 milliseconds, I guess. And then you compute the Fourier transform of the data only in this 500 milliseconds, ignoring everything else in the signal. Then you take the Fourier transform of this little time window, and here you see the power spectrum of these data, so this little snippet of data, this window of data. And then you would take this and then rotate this power spectrum, so frequency is now on the y-axis, and then you color code this so that the power would be sort of in the depth or the color axis. And then that gives you one line of frequency in this time frequency plane. And so then the location of this line would be at the center of this time window. So here it would be like 200 milliseconds or whatever. Okay, so or 250 milliseconds, I guess. So I think that makes intuitive sense. And then the idea is this only tells you about the spectral characteristics in this time window, but of course you want to populate this entire time frequency space. And so what you would do then is take this window and just move it across by some number of milliseconds. So let's say 50 milliseconds or 10 milliseconds. You move this window over and then do the same procedure, do the Fourier transform, take the power spectrum and then plot it here, and then this would give you a second bar over here. And you keep doing this again over and over and over for many time windows, and then you fill up this time frequency space. So that's very straightforward. There's a few things that we can talk about just to fill in the details. One is that it's important to taper the data somehow. Now, tapering is something you've already been introduced to with wavelets. So the way you create a wavelet, or Morley wavelet, is by taking a pure sine wave and tapering it, or pointwise multiplying it by a Gaussian. Here, the reason why we want to taper the data is to avoid getting edge artifacts into the frequency representation. And now we've seen edge artifacts both from the time domain going to the frequency domain and from the frequency domain going back into the time frequency reconstruction. Here the issue is that there could be edge artifacts at the edges here where we cut the windows. And so we apply a taper to these data to attenuate the signal going out into the edges, and this basically avoids edge artifacts. Now, of course, we are also attenuating real signal. This is real signal, and we're dampening it here. And so this means we are losing signal by doing this. And so the way that you would account for this, the way that you would recover this lost signal due to tapering, is by moving this window in time steps that are smaller than the entire time step. So if you would move this, or the entire time window. So if you would move this time window by 100 milliseconds, then you'd see that the signal that is attenuated here is less attenuated when we move the window over, because that signal is closer to the center. So let's see, there's a few other things I want to say, but we can do this in MATLAB. So here is some code for a very simple short-time Fourier transform. I will discuss in a few minutes how this could be made more sophisticated for real data analysis. This is kind of a simplified version just to give you a sense of how it works. So we load in the data. We're going to pick an electrode. Here I picked 01. You can change this. Here, this variable times to save. These are the time points, the center time points of the windows that we are going to use. So you can see that we are going to skip forward in 25 millisecond steps. This again is for the decibel normalization, and this is the variable time when this is our key variable for defining the widths of the time window. So here in the PowerPoint slide, I had 500 milliseconds, and here in the code I have 300 milliseconds. We will change this around and see what the effect is. Okay, so you can look through all of this stuff. This is most of this is somewhat standard now. This is the Hahn taper, which, well, I'll show you what it looks like in a minute, actually. It just looks like half a cosine, actually, as you can already guess from looking at the function. So here is the meat of the short-time Fourier transform. So what we're going to do is loop through time points, and then here we take the data. So this is a really long line, but if you break it down, it's actually not so many things happening in this line. So we take the EEG data from this channel and from this particular time window, so starting at the center time point, and then we go back half the length of the window, and then we go back to the center time point, and then we go forward half the length of the window. And here's the Hahn taper, and I'm using this BSXFun function to multiply and expand and multiply the Hahn taper with the data. So that gives us our kind of temporary data. Then I take the FFT of the data, compute the power here, and then average over trials. And now here we don't need to save every single frequency. We are only going to save some frequencies, and in particular we are going to save frequencies between 10 Hertz and 1/5 of the sampling rate in 20 steps. Now, of course, with the Fourier transform, we can extract frequencies up to the Nyquist frequency, which is half of the sampling rate. So, in theory, we could validly go up to the Nyquist frequency. But in general, the higher you get in frequency, the lower the signal to noise is going to be, in part because EEG and MEG is not really able to reconstruct a lot of neural activity going, above like sort of 80 or 150 hertz or so, and in part because once you get close to the Nyquist frequency, you just get very few sample points, very few measurement points, so the signal to noise becomes very low. Let's see, so we're not going to extract all the frequencies, but only some of the frequencies. Then we do decibel normalization here, and then we plot the results. So let's see how this looks. Here we see our time frequency plot. You can see already it's a little more blocky relative to what you are now used to seeing with complex Morley wavelet convolution. This is basically because the time bins are moving forward in steps of 25 milliseconds, and the frequency resolution is not really that great here. If you remember back to the lectures on the Fourier transform, then you'll remember that the frequency resolution of the Fourier transform is defined by the number of time points in the time domain signal. And so this parameter here, the length of the window of time, is the key parameter that is defining the frequency resolution. So we can change this to, let's say, I don't know, 800 milliseconds. That's maybe a little bit extreme. And now watch what happens to the plot here on the right side of the screen. Now you can see the plot changed noticeably. So what's happened now is we've gotten much better frequency precision, but much worse temporal precision. And we got better frequency precision because we have more time points in our FFT. But of course the the time precision decreased because now we are averaging over all the dynamics within a time window of 800 milliseconds, which is quite a big chunk of time. I mean, actually this, I'm only plotting here from 0 to 800 milliseconds. And so the estimate of activity at 400 milliseconds is influenced by activity going all the way back to 0 and all the way forward to 800. So this is perhaps a bit of an extreme value for a fast task like this. But this just gives you an idea. So we can take the other extreme here and go down to 100 milliseconds. This is also a pretty poor choice of a time window, in part because the sampling rate is only 256 hertz. But you can see now we have much better temporal precision, but really awful frequency precision. In fact, a lot of these are overlapping points. So really, it looks like we only have 1, 2, 3, 4, 5 actual frequencies that we are able to reconstruct here. And this signal down here looks particularly uninformative. And this should actually make sense when you think about it, because our time window is 100 milliseconds. And the lowest frequency that we are trying to extract from the data is 10 hertz. So 10 hertz means one cycle every 100 milliseconds. So this means we are only able to estimate one cycle of activity here at this lowest frequency, which is technically possible, but it gives us very, very poor signal to noise. So this is really not a good parameter value for this, given this sampling rate and these frequencies that we are interested in. Okay, so I think 300 is okay. Let's see. Oh, it's going to show you the Han taper, so you can see what that looks like. Han. So you can see that's just tapering. The data, it starts and ends at 0, and it peaks at 1. It looks a lot like a Gaussian. It's formally not exactly a Gaussian. You could use a Gaussian window here, or a Hamming window, or Blackman window. There are all sorts of windows that you can use. You can compare these different windows as long as you use some kind of window taper. It doesn't really matter exactly which taper you use. But now I'd like to show you the difference that you will see without doing any tapering. So if you uncomment the line on 42, then this is basically the same as the line as line 40, except here we are not doing any tapering. So we're just going to look at the data without applying any tapering. So you can look at figure 1 here now while I run this, and you'll see the difference that tapering makes. So you can see it makes quite a big difference. And now we get a lot of these these sort of ripples, these repeated features that come up. And this doesn't really look physiologically plausible to have these frequency characteristics bursting like this at the trial average level. These are basically edge artifacts that have resulted from us failing to apply any kind of taper to the data. So you can see some aspects of the data are sort of, more or less preserved, but this is really not a interpretable result. This is much more interpretable. All right. So what we have done in this simple code here is keep the sizes of the time frequency tiles the same over all frequency bins. this is fine. There's nothing wrong with that. This is actually kind of the original method for doing short-time FFT. But you can get slightly nicer looking results by changing the size of these windows as a function of frequency. And so here you see this is an illustration of how for different ranges of frequencies, so we have kind of low frequencies and medium frequencies and high frequencies. For different ranges of frequencies, you could use different time windows. And this is a way to try and balance the trade-off between time precision and frequency precision as a function of increasing frequency. This is analogous to changing the number of wavelet cycles with increasing frequency. I took this picture from the Field Trip website, I think from one of their tutorials. So now you've learned 3 different methods for extracting time frequency information: Morley wavelet convolution, filter Hilbert, and short time FFT. Maybe you're wondering, do these things really give me different results, and does it matter which one I use, and which one should I use? Well, it turns out you were not the only person to have asked this question. This was assessed directly, actually in several papers, but to my knowledge, this one was the first. And this is really the question of this paper. Fourier and Hilbert and wavelet-based signal analysis, are they really different approaches? In fact, you can infer just kind of analytically that these are going to give you the same results. Because, for example, I've already discussed that that filter Hilbert and wavelet convolution can give you pretty much exactly the same result if you construct the filter kernel to have a Gaussian shape in the frequency domain, which is exactly what the shape of a Morley wavelet is. Anyway, here you see results for different parameters, different time frequency parameters. And here are the results for the short time Fourier, filter Hilbert, and Morley wavelet convolution. And you see, of course, there are a few very subtle differences between them, but overall the signal characteristics are very, very similar. And in fact, you could modify these parameters. You could tweak the parameters a bit more to get these results to be even more similar than they are. I suspect eventually Andreas Bruns just got... he probably just got sick of tweaking this around, maybe 1.102, so he just left it at this. But the point is that overall these different methods are going to basically give you the same results at the broad scale. Here you see plots of correlation coefficients between these different pairs of results. So this is the short time Fourier and filter Hilbert. This is the short time Fourier transform and wavelet convolution, and so on. And here you see the different parameters. These are basically just the width of the frequency domain response. And these plots show correlations. So you might think, well, these are the high correlations, and then once the parameters start changing, then you get to lower correlations. But actually, if you look at this plot, the correlations go up to 1, so the saturated black color gets to 1. And even, this white color is 0.9. So even, out here, when you get more sort of more noticeable differences between the results, the differences are not that huge. So this is actually nice to know, because it means that the choice of method for decomposing your time domain signal into the time frequency domain is not really that important. In fact, I think it's fair to say that the parameters you choose within any given method are going to be more consequential than choosing different kinds of methods. And so which method you pick doesn't really matter. It mainly depends on what you feel most comfortable with, and what you sort of, I'll just stop there, what you feel most comfortable with. I think I mentioned in the previous lecture that I personally feel most comfortable with Morley wavelet convolution, and that's really just because it's harder to get it wrong, because there aren't that many parameters. It's always going to be a Gaussian in the frequency domain. It generally always produces good, solid, trustworthy results. With filter Hilbert, you have to be a bit more careful about parameterizing the filter characteristics and things. And so, yeah, well, I believe that's all I have to say about that. And I hope you found that informative. See you in the next lecture.